What if every volcano on Earth erupted at the same time? At 2:17 in the morning, Dr. Nia Okafor is watching a quiet line move across a monitor in a dark operations room in Colorado. The line represents seismic activity beneath a volcano in Alaska. It has been almost unchanged for 3 hours. On another screen, colored dots mark monitored volcanic systems across the world. Most are green. A few are yellow. 2 are orange. Nia has worked with volcano data for 19 years. She knows that the Earth is never completely still. Small earthquakes happen constantly. Magma shifts beneath some volcanoes without producing an eruption. Gas escapes through cracks. Ground rises by a few millimeters and falls again. A quiet planet would be stranger than the moving one she studies. Then every dot changes color. The first alarm is followed by another before she can reach the keyboard. Then dozens. Then hundreds. The room fills with overlapping tones. Seismic stations in Alaska, the Cascades, Mexico, the Andes, Iceland, Italy, East Africa, Indonesia, Japan, Kamchatka, New Zealand, and remote islands begin reporting sudden movement beneath volcanic systems that have never behaved together before. Nia assumes a software failure. A global database has corrupted its timestamps. A satellite feed has duplicated a warning. Someone has pushed test data into the live network. She opens the raw signal from Mount Rainier. The earthquakes are real. She checks Mount Etna. Real. Popocatépetl. Real. Merapi. Real. A submarine monitoring station near the Mariana Arc reports pressure waves in the water. Instruments in Iceland show rapid ground deformation across several separate systems. Gas sensors near active craters begin rising beyond their normal ranges. At 2:18, cameras around the world capture the first plumes. At 2:19, a colleague says the sentence nobody in the room believes. They are all erupting. The thought experiment begins there. In reality, this cannot happen. Volcanoes do not share one global chamber waiting beneath the crust. Their magma systems are separate, shaped by local pressure, temperature, water, gas, rock, and tectonic conditions. Even neighboring volcanoes can have independent reservoirs. An eruption on one continent does not trigger another thousands of kilometers away. So our story needs one impossible rule. At the same instant, every active or potentially active volcanic system with a living magma source begins an eruption. That includes volcanoes that erupt often, volcanoes that have slept for centuries, calderas monitored because they may erupt again, and many volcanic systems beneath the oceans. Mountains whose magma supply ended millions of years ago remain silent. An eroded extinct volcano cannot produce magma merely because it still has a name. The second rule is equally important. Every volcano erupts according to the system it actually possesses. A small basaltic vent does not suddenly become a supervolcano. A shield volcano may pour out fluid lava. A stratovolcano may explode, collapse, or produce ash and pyroclastic flows. A caldera system may release a major eruption, but not necessarily the largest eruption it has ever been capable of producing. Many submarine eruptions remain partly confined by the immense pressure of deep water. The event is not every volcano producing its maximum imaginable disaster. It is every volcano producing an eruption at once. That is enough. At 2:20, the first global satellite images begin to change. Across the Pacific Ring of Fire, columns rise from the Aleutian Islands, Kamchatka, Japan, the Philippines, Indonesia, Papua New Guinea, New Zealand, the Andes, Central America, Mexico, and the western edges of North America. The line is not a perfect ring, and the eruptions are not identical. Some plumes are white with steam. Some are black with ash. Some volcanoes open glowing fissures that stretch across the ground. In Hawaii, lava fountains rise above new cracks. In Iceland, several fissure systems split through old lava fields and snow. In the Andes, explosive columns climb through the thin air while ice begins melting from summit glaciers. At Vesuvius and Campi Flegrei, alarms wake millions of people in southern Italy. In Java, sirens overlap from communities living near several volcanoes at once. In the Cascades, Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens, Mount Adams, Mount Hood, and other systems begin shaking within the same minute. No emergency plan was designed for every evacuation zone to activate together. Nia calls her son. Eli is 22 and studying civil engineering in Portland, Oregon. He moved there 6 months earlier, close enough to see Mount Hood on clear mornings. Nia had spent years teaching him that living near volcanoes did not mean living in constant danger. His phone rings once. Then the network fails. She sends a message telling him to stay indoors, fill every container with water, protect his lungs from ash, and follow local emergency instructions. The message remains undelivered. Around the world, the first people to understand the event are those living closest to volcanoes. They do not see a global map. They hear windows shaking. They smell sulfur. They watch animals run. Some receive warnings from monitoring agencies. Others see an eruption begin without the usual days or weeks of escalating unrest because the impossible trigger has compressed the buildup into seconds. Near the most explosive volcanoes, survival depends on distance and topography. Pyroclastic flows descend from collapsing eruption columns and unstable domes. They are not ordinary smoke. They are dense avalanches of ash, gas, and rock, hot enough to ignite material and fast enough to outrun vehicles on many roads. Valleys guide them outward from volcanic slopes. In some places, communities inside mapped danger zones have minutes. In others, they have none. Snow and ice melt from high volcanoes. Water mixes with ash and broken rock to form lahars, volcanic mudflows that follow river valleys far beyond the places reached by lava. Bridges disappear. Roads are buried. Towns that cannot see an eruption hear a roar approaching through darkness. Lava receives the most attention in films because it glows. In the first hour, it is not the greatest global danger. Most lava flows move slowly enough for people to escape if routes remain open. The immediate killers are pyroclastic flows, collapsing slopes, lahars, falling rock, toxic gas, fires, and the failure of buildings beneath heavy ash. The first 10 minutes are local catastrophes repeated across the planet. That repetition creates the global disaster. At 2:31, aviation authorities begin closing airspace. An aircraft can fly around one ash cloud. It cannot easily fly around thousands. Volcanic ash is not soft material left after a fireplace burns. It consists of tiny sharp fragments of rock, minerals, and glass. Inside a jet engine, particles can melt, stick to components, and cause loss of thrust. Ash can abrade windscreens until pilots can no longer see clearly. It can damage instruments, sensors, and moving surfaces. Commercial aircraft already in the air receive diversion instructions. The instructions change as new plumes appear. Airports once considered safe alternatives close within minutes. Pilots descend toward runways under skies becoming darker. Some aircraft land in regions far from volcanoes. Others cannot reach them before ash crosses their routes. For the first time in aviation history, the safest general instruction becomes simple. Land every aircraft that still can. At sea, crews report columns rising from islands and shallow submarine vents. Some undersea eruptions create floating pumice rafts. Others send discolored water and steam across the surface. The oceans do not boil. Most of the seafloor lies beneath pressure strong enough to suppress the explosive expansion of gas. Deep submarine lava chills rapidly against seawater and forms new rock. Many underwater eruptions would remain invisible from ships passing far above. Yet shallow water systems behave differently. where eruptions displace water, collapse volcanic flanks, or trigger submarine landslides. Regional tsunamis spread outward. They do not merge into one wall of water circling Earth. They arrive as many separate waves at different coastlines, some destructive, some barely noticeable. Coastal warning centers attempt to calculate thousands of sources at once. Their models were built for events that can be isolated. The planet is no longer offering isolated events. At 2:45, the lights flicker in Nia's operations room. The center has backup generators, filtered air, stored water, and satellite communication. It was built to remain functional during regional disasters. Nothing about it was built for the simultaneous failure of airports, roads, power stations, observatories, and communication links around the world. Nia's team stops trying to confirm whether every alert is real. They begin asking a different question. What is still working? Seismic stations continue transmitting from some regions. Others vanish from the map as power fails or cables break. Cameras go dark. Gas instruments exceed their measurement limits. Satellites remain the broadest view, but even their images become difficult to interpret as plumes overlap. The first world map produced by the emergency team looks less like a scientific display than a weather image of a planet on fire. It is misleading. Most of Earth is not burning. Vast regions lie far from volcanoes. Continents are not splitting open everywhere. Lava is not flowing across every city. The solid crust remains beneath farms, deserts, plains, and forests. But the atmosphere connects places the ground does not. Wind begins carrying the event outward. Ash rises from explosive eruptions and spreads downwind. Heavy fragments fall near vents. Fine particles travel hundreds or thousands of kilometers. Sulfur dioxide climbs with the strongest plumes toward the stratosphere, where rain cannot remove it quickly. During an ordinary eruption, scientists watch one cloud expand. Now every major wind system receives ash and gas. The atmosphere becomes the place where separate eruptions begin to combine. At 3:06, Eli's message reaches Nia. It contains only 4 words. I am inside. Breathing okay. She reads it 3 times. Then the signal disappears again. Outside the operations center, Colorado remains dark and cold. No nearby volcano has erupted. The mountains on the horizon look unchanged. For the moment, the air is clear. Nia understands that this may be one of the safest places on Earth. She also understands that safety will soon depend on things no mountain can provide. Food, water, power, heat, medicine, and sunlight. By sunrise, the word eruption has become too small. A normal emergency map uses symbols to separate hazards. Red for lava, gray for ash, blue for tsunami, brown for lahars, yellow for gas. On this morning, the colors cover one another. The first global consequences are not evenly distributed. People living near explosive volcanoes face destruction immediately. People in continental interiors may see nothing unusual for hours. Some island communities lose ports and airfields before they receive a complete warning. Cities far from volcanoes remain physically intact while discovering that almost every route connecting them to the outside world has closed. The event punishes geography, but it also punishes dependence. A village beside a dormant stratovolcano may be destroyed in minutes. A distant megacity may survive the eruption and still lose water because pumps fail, food because trucks stop, and medicine because aircraft cannot fly. Nia's operations room becomes part volcano center, part weather office, part logistics hub, and part archive. She assigns one team to identify the largest explosive columns. Another tracks sulfur dioxide. Another maps power failures. A fourth tries to estimate which major agricultural regions lie downwind of thick ash. The numbers change too quickly to summarize. Indonesia has more erupting systems than the staff can discuss individually. Japan is managing simultaneous evacuations across several islands. Ecuador, Colombia, Peru, and Chile report ash over mountain corridors. East African volcanic fields produce fissures and gas emissions. Mediterranean airspace disappears beneath overlapping warnings. Iceland's eruptions sever roads and damage power infrastructure while also releasing large volumes of gas. Some famous volcanoes produce surprisingly modest eruptions. Some obscure ones become deadly. This is a crucial fact about the scenario. Fame is not energy. A volcano known from history is not automatically the largest threat today. A little-known system may contain pressurized magma, steep, unstable slopes, a crater lake, or communities built directly along lahar channels. The world's attention cannot focus on one mountain. There are too many. By mid-morning, ash has begun falling on Portland. Eli seals the edges of his apartment windows with tape and wet cloth. The city has emergency instructions for ashfall, but residents are receiving warnings from several directions. Mount St. Helens has sent a plume east and south. Mount Hood's column bends with upper winds. Smaller amounts arrive from farther systems. The sky becomes brown before noon. Streetlights turn on automatically. Cars move slowly with headlights glowing through the haze. Air filters clog. Some engines stall. People rush toward shops until authorities tell them to stop driving unless absolutely necessary. Eli fills the bathtub, pots, bottles, and a plastic storage box with water. The tap pressure weakens while he watches. Ash falls silently. It does not arrive like snow, although the city first looks as though winter has come. Snow melts. Ash remains. It scratches glass. It enters doorways. It turns to heavy paste when rain begins. On roofs, weight increases. Flat commercial buildings are especially vulnerable. Gutters block. Water collects. Several roofs collapse before residents understand how much wet ash can weigh. Electrical faults begin across the region. Ash coats insulators and equipment. Moisture helps current travel where it should not. Transformers fail. Repair crews cannot reach every site because roads are slippery, visibility is poor, and engines need constant filter changes. Eli receives a city alert instructing residents to conserve water. He looks at the containers surrounding him and thinks of his mother's message. For the first time since moving away, he wishes she had taught him less science and more certainty. There is none. Across the world, hospitals close air intakes and move vulnerable patients away from windows. Staff distribute masks. Emergency rooms fill with people suffering from ash irritation, injuries, burns, and panic. Volcanic ash is dangerous to lungs, especially for people with respiratory illness, but it is not usually a poison that kills everyone who breathes a trace. The problem is concentration, duration, sharp particles, and the collapse of systems people need to protect themselves. Masks help. Clean indoor air helps more. Neither is available equally. Communities with strong buildings, filtered ventilation, stored supplies, and functioning government fare better. Informal settlements near volcanic slopes fare worse. Prisons, refugee camps, nursing homes, hospitals, and remote villages face dangers that evacuation plans often underestimate even during one disaster. Now every region is competing for the same emergency resources. There are not enough aircraft because aircraft are grounded. There are not enough filters because factories and warehouses cannot distribute them. There are not enough volcanologists to interpret every system, and many have lost access to their own observatories. The scientific problem becomes tree-off. Which eruptions are still escalating? Which slopes are collapsing? Which rivers will carry lahars? Which plumes are reaching the stratosphere? Which warnings can still save people? The first day also reveals what does not happen. The Earth does not crack apart. The planet does not leave its orbit. The magnetic field does not vanish. Volcanoes release enormous energy, but they are surface expressions of local geological processes, not engines capable of exploding the planet. No chain of lava joins every volcano. No single earthquake circles Earth and knocks down every city. Many earthquakes occur as magma moves, rock fractures, and volcanic structures fail. Nearby tectonic faults may also respond in some regions, but the combined event does not behave like one global impact. The disaster is vast because thousands of regional catastrophes happen together, not because the entire planet becomes one volcano. That distinction matters to survival. Most humans are not standing inside pyroclastic flow zones. Most buildings are not struck by lava. Most land remains physically habitable on the first day. The great danger shifts from direct eruption to the networks connecting civilization. At noon, global commercial aviation has nearly stopped. Major shipping routes remain open in places, but ports near volcanic coasts close. Ash reduces visibility and contaminates machinery. Pumice rafts clog some harbors. Tsunami warnings delay coastal operations. Railways become more valuable, then begin failing where tracks are buried, power is lost, or bridges are damaged by lahars. Road transport slows under ash. Diesel engines continue longer than many gasoline vehicles, but filters require replacement. Fuel deliveries stop. Emergency agencies reserve remaining stocks. The internet does not simply disappear. Submarine fiber cables continue carrying data in many regions. Data centers far from eruptions remain active if they have power and cooling. Satellites relay emergency communication. Local networks, however, fail as towers lose electricity and ground equipment is damaged. The world remains connected in fragments. People can see disasters they cannot reach. Videos show lava fountains in Iceland, darkness over Java, lightning inside ash plumes in the Andes, and orange skies over Italy. Some clips are real. Others are old footage mislabeled within minutes. Rumors claim that the oceans are boiling. They are not. Rumors claim Yellowstone has exploded with the greatest eruption in its history. It has not. The Yellowstone system is erupting in this impossible scenario, but the event is smaller than the caldera-forming eruptions preserved in its geological record. Geyser basins are disrupted. Hydrothermal explosions and ash affect the region. Roads close. Wildlife flees. The eruption is serious. It does not bury half a continent beneath meters of ash. The same is true at other caldera systems. The premise forces eruption, not unlimited stored energy. This does not reassure the public. A lie needs one dramatic sentence. The truth needs explanation while the sky is dark. Nia appears in a satellite interview that reaches millions of people. The journalist asks whether humanity is facing extinction. She answers that she does not know. The honest response causes outrage. She continues, "Most people are not in the direct path of volcanic flows. The atmosphere will cool. Agriculture will be severely disrupted. Transport and power systems are failing. Survival will depend on cooperation, food reserves, protected energy, and the duration of stratospheric aerosols." The journalist asks for a number. Nia refuses to invent one. Behind the camera, one of her colleagues raises a hand. A new sulfur estimate has arrived. The largest eruption columns have injected gas high above weather systems. Winds are beginning to spread sulfate, forming material around both hemispheres. The climate effect will not be the ash cloud visible from the ground. Most ash falls out in days or weeks. The longer shadow will come from sulfur dioxide transformed into tiny sulfate droplets in the stratosphere. These particles reflect sunlight and can remain for years. One large eruption can measurably cool the planet. This morning has produced many. Their effects cannot be added like simple numbers. Some plumes remain too low. Some sulfur is removed quickly. At very high sulfur burdens, aerosol particles can grow larger, settle differently, and make each additional unit of sulfur less efficient at cooling the surface. Recent modeling also suggests that global mean cooling may begin to saturate while rainfall continues to decline. Even with those nonlinear limits, the first climate models produce a conclusion no one wants to say aloud. The next growing season may not resemble any in modern history. At 5:40 in the afternoon, Nia receives another message from Eli. Power out. Water stored. Building holding. She replies with one instruction. Do not go outside to clear the roof alone. He answers. Wasn't planning to. The humor is small, but it is alive. Night arrives twice over Portland. The first darkness is ash. The second is sunset. Across the world, millions of people sleep in evacuation centers, cars, tunnels, schools, stadiums, and rooms sealed with towels. Others do not sleep at all. The eruptions continue. Some will last hours. Some will last months. A few will continue for years. The impossible synchronization happened in one moment. The consequences have only begun to separate in time. The second day is quieter in a way that makes the disaster feel larger. Fewer new alarms sound because almost every system is already in eruption. The operations center no longer reacts to beginnings. It tracks continuation, collapse, and loss. Morning satellite images show the atmosphere divided into layers. Near the ground, ash spreads in irregular bands shaped by local winds, mountains, and rain. Some cities a few hundred kilometers from volcanoes receive heavy deposits. Other places closer to vents remain briefly clear because the wind carries plumes away. Higher above, sulfur-rich clouds move across national borders without recognizing emergency declarations. At the surface, the most dangerous flows remain local. Pyroclastic currents continue around explosive volcanoes. Lahars surge through valleys after rain and melting ice. Lava cuts roads and burns structures. Gas collects in low areas. Crater lakes overflow. Volcanic slopes, destabilized by earthquakes, collapse without warning. The first day's evacuation maps are already outdated. At some volcanoes, activity weakens quickly. At others, the eruption intensifies after the first release opens pathways for deeper magma. This is another reason the catastrophe cannot be summarized by counting volcanoes. 1,000 small eruptions do not equal 1,000 large eruptions. Volume, sulfur content, plume height, latitude, season, water interaction, and duration matter more than the number of red dots. Nia's team begins classifying the event by atmospheric influence. Category 1 includes eruptions mostly confined to lava and low plumes. Category 2 includes regional ash producers. Category 3 includes eruptions reaching the upper troposphere. Category 4 includes major stratospheric injections capable of changing global climate. There are far too many in Category 4. The team stops publishing the complete list because the list is misread as a ranking of human importance. A smaller eruption beside a dense city may kill more people immediately than a larger remote eruption that changes climate for everyone later. Emergency planners need both scales at once. The near world is burning. The far world is dimming. By the third day, the planet's sunsets become extraordinary. Where clouds are thin enough to see them, the horizon glows red, purple, and copper. Sulfate aerosols scatter light around the curve of Earth. Photographs spread through surviving networks. People call the skies beautiful. Many feel guilty for saying so. Beauty does not cancel disaster. Disaster does not make every physical effect ugly. Nia steps outside the operations building for the first time in 50 hours. The Colorado sky is hazy but still blue overhead. The sun appears through a pale veil. She holds a mask against her face. Ash from western eruptions has begun reaching the region in small amounts. Cars in the parking lot carry a dusty gray film. The mountains are still visible, but their edges have softened. She calls Eli through an emergency satellite relay. His voice arrives broken into fragments. His apartment building has power for 40 minutes at a time from a shared generator. City crews are clearing hospital routes. Water is being distributed from protected reservoirs. The ash on his street has reached several centimeters and becomes mud whenever rain falls. He asks whether he should leave. Nia cannot answer without knowing the route, vehicle, wind, bridge conditions, shelter capacity, and eruption behavior around the Cascades. A person can be safer inside a damaged city than on a road passing through Lahar valleys. She asks what local authorities are saying. Stay indoors unless assigned evacuation. Then stay. He is silent. You always have a better answer than that. Not today. The truth frightens him more than false confidence would have. It also gives him something solid. By the fourth day, food begins disappearing from urban shelves. The problem is not that the planet has run out of food. Warehouses contain grain. Farms contain animals. Ports hold containers. Cold storage facilities contain meat, vegetables, and medicine. The problem is movement. Modern cities keep limited supplies close to consumers because transport normally arrives continuously. When aircraft stop, roads close, ports fail, power becomes unstable, and workers remain home. Abundance in one region cannot easily relieve shortage in another. Governments introduce rationing. Some do it before panic buying empty stores. Others wait. Military units guard distribution centers. Local councils convert schools into kitchens. Restaurants donate food before refrigeration fails. Families cook frozen supplies together. In wealthier regions, the first shortages are inconvenient. In poorer regions already dependent on imports, they are dangerous immediately. Countries that export grain suspend contracts to protect domestic supply. Importing nations protest. Global food markets freeze because prices no longer describe whether a shipment can physically move. The United Nations calls for an emergency agreement preventing complete export bans. Some governments cooperate. Others calculate that promises will not feed their own citizens if the crisis lasts years. The event tests the difference between national responsibility and collective survival. Every country can protect its own reserves for a while. No country produces every crop, medicine, machine part, fertilizer, and fuel it needs. The first major political conflict begins over grain before any war begins over territory. At the same time, agriculture is already being damaged in the fields. Ash coats leaves and reduces photosynthesis. Heavy deposits flatten crops. Livestock lose access to clean pasture and water. Machinery fails when abrasive particles enter engines. Greenhouses survive better where roofs hold and filters remain available. Some ash is chemically harmless after weathering. Some contain soluble fluorine or other compounds that contaminate water and poison grazing animals at sufficient concentrations. Farmers cannot wait for laboratory results from every eruption. They move animals, cover water tanks, and clear roofs while breathing through masks intended for one emergency, not months of exposure. Rain creates another problem. It washes ash from the air, improving breathing temporarily. It also moves ash into rivers, reservoirs, drains, and water treatment systems. Ash is not dissolved dirt. It is abrasive material that settles, clogs, and damages pumps. Treatment plants can remove it if they function, but demand rises as equipment becomes harder to maintain. Cities begin separating water by purpose. The cleanest supplies are reserved for drinking and hospitals. Lower quality water is used for washing and toilets. Fire services struggle because hydrant pressure falls while volcanic lightning, broken electrical lines, and lava ignite fires. The atmosphere becomes darker over the following week. Not everywhere. Weather still creates clear regions. Wind shifts. Rain removes lower ash. Some communities see blue sky and wonder whether the crisis has been exaggerated. Then upper-level haze reaches them. The sunlight changes first. It loses sharpness. Shadows soften. Solar panels produce less electricity even where no ash covers them. Temperatures begin falling beyond normal weather variation. Climate models now agree on the direction and disagree on scale. The eruption mixture is unlike any event observed by instruments. Scientists understand individual processes. They do not possess a direct historical example of hundreds of simultaneous stratospheric injections in both hemispheres. The early models estimate global average cooling ranging from 3 to 8 degrees Celsius during the first peak. Because no real event resembles this one, the range is a scenario envelope, not a forecast that could be assigned a reliable probability. It is not a minor uncertainty. 3 degrees would devastate agriculture. 8 would transform seasons across much of the planet. Nia refuses to choose the most dramatic model for public briefings. She also refuses to choose the mildest. The actual result will depend on how long the largest eruptions continue and how aerosols spread. The public wants certainty before making decisions. Science can provide warning without certainty. That becomes enough for governments to act. Seed banks are secured. National grain reserves are counted. Protected agriculture facilities receive priority power. Nuclear plants, hydroelectric stations, geothermal systems, gas facilities, wind farms, and remaining fossil fuel plants are assessed for ash vulnerability. Solar power declines sharply. Wind turbines continue in clearer regions, but suffer abrasion and maintenance problems. Hydroelectric intakes face sediment. Thermal plants struggle with air filters. No energy source is untouched. Some are more resilient than others. Regions with diversified grids fare better than those dependent on one technology. Iceland loses infrastructure near eruptions, but retains valuable geothermal heat where systems remain intact. France protects nuclear generation from ash contamination. Countries with underground gas storage preserve heating. Remote communities with microgrids disconnect from failing national networks. The world discovers that resilience is not the same as efficiency. The most efficient system during normal years often contains little spare capacity. The system that survives catastrophe contains redundancy that once looked wasteful. Eli's apartment generator stops on day 6. The building becomes cold at night. Portland's temperature has fallen, but not yet severely. Residents gather in interior rooms. A retired nurse organizes checks on older people. Eli helps construct a filtered air space in the lobby using plastic sheeting, tape, fans, and replacement filters collected from several apartments. His engineering education becomes practical in ways no class intended. On day 7, city officials assign him to a roof clearing team. They work in harnesses because wet ash is slippery. They remove material gradually to avoid shifting loads. One warehouse roof nearby has already collapsed. Eli sends Nia a photograph of himself covered in gray dust except for the outline around his goggles. She replies that he looks irresponsible. He replies that he looks employed. This time the humor survives transmission. Other messages do not. Nia receives lists of observatory staff who have died or disappeared near volcanoes they spent their careers studying. Some remained to maintain instruments during evacuation. Some were caught by roads closing behind them. Some were at home inside danger zones when the simultaneous trigger arrived without warning. The scientific community loses people at the moment their knowledge is most needed. Their records remain. Hazard maps created years earlier guide evacuations. Models built for single eruptions are adapted. Local studies of valleys, winds, slopes, and past deposits become more valuable than global speculation. There is no universal volcano. Every saved life depends on someone having studied one place carefully before the world cared about it. By the end of the first week, the immediate global death toll is already beyond reliable counting. Many deaths occur close to volcanoes. Others come from tsunamis, fires, building collapse, respiratory emergencies, interrupted surgery, failed transport, and violence during evacuation. It is still too early for famine. It is not too early for hunger. The eruptions continue under a sky that reflects more sunlight each day. The next phase will not be measured in alarms. It will be measured in harvests that never arrive. The first month changes the meaning of weather. Forecasts still show fronts, rain, wind, and pressure systems. Meteorologists continue tracking storms. Yet every forecast now contains a second layer describing the volcanic veil above ordinary clouds. Daylight weakens gradually enough that people adapt before realizing how different it has become. At noon, the sun appears pale. At dawn and dusk, the sky burns with color. At night, temperatures fall quickly where clouds are absent because the surface absorbed less energy during the day. The cooling is not uniform. Continents cool faster than oceans. Northern land areas entering autumn lose heat rapidly. Tropical regions remain warmer but receive less sunlight. Monsoons weaken or shift. Rainfall patterns change in ways that are harder to predict than temperature alone. Some places become colder and drier. Others receive unusual storms because temperature differences redirect atmospheric circulation. The phrase volcanic winter suggests one simple season covering the planet. The reality is a broken climate. NIA's team merges with climate centers, agricultural agencies, and energy planners. Volcano names slowly disappear from daily meetings. The questions now concern sunlight, frost dates, reservoirs, calories, and grid stability. The eruptions created the crisis. The atmosphere is carrying it forward. By the sixth week, global average temperature has fallen by nearly 2 degrees Celsius. This is only the beginning. The strongest cooling occurs over large northern continents. Snow arrives early in Canada, northern Europe, Russia, and parts of Central Asia. Frost damages crops weeks before harvest. Mountain regions already coated in ash receive snow that hides unstable deposits and later creates new mud flows during brief thaws. In tropical agriculture, cold is not the only problem. Reduced sunlight lowers growth. Rainfall becomes unreliable. Coffee, cacao, bananas, rice, and other crops respond differently, but almost none benefit from sudden darkness and disrupted transport. Ocean surface temperatures fall more slowly. This gives coastal regions some protection while also changing storms and marine ecosystems. Governments begin measuring survival in stored calories. Wheat, rice, maize, soy, potatoes, and other staples are counted not by market value, but by how many people they can feed through a failed year. Animal feed becomes a moral and economic decision. Grain used for livestock could feed humans more directly. Herds cannot all be maintained. Mass slaughter begins in some regions, not because meat demand rises, but because feed and clean water cannot be guaranteed. Cold storage systems struggle with unreliable electricity. Food spoils while people are hungry. The contradiction becomes one of the defining images of the catastrophe. An emergency agricultural council develops a global plan built around 4 priorities. Protect existing grain. Shift fields toward cold-tolerant, fast-growing crops. Move production indoors where energy allows. Reduce waste at every stage. The plan is scientifically reasonable. Implementation depends on politics, fuel, machinery, labor, and trust. Farmers cannot instantly replace one crop with another. Seeds must exist in the right quantity. Soil may be buried beneath ash. Tractors need filters and fuel. Workers need food while producing food. Some regions possess seed reserves and extension services capable of rapid change. Others receive instructions without resources. Greenhouses become strategic infrastructure. Ordinary glass structures are vulnerable to ash weight and reduced sunlight. Governments reinforce roofs, install artificial lighting, and convert warehouses into controlled farms. Mushrooms, algae, potatoes, leafy vegetables, and rapidly reproducing microorganisms receive enormous investment. These systems cannot feed the world immediately. They can preserve nutrition, produce seed stock, and support hospitals and cities. Electricity becomes food. A kilowatt can operate a pump, a lamp, a heater, a refrigerator, or a communication system. Every use competes with another. Nuclear plants in stable regions become especially valuable because they do not depend on sunlight or constant fuel delivery, though they still require cooling water, staff, spare parts, and clean air systems. Geothermal plants survive in some volcanic countries and fail in others where eruption damage reaches wells and pipelines. Wind remains useful where ash abrasion can be managed. Coal and gas plants increase production in several countries despite long-term climate commitments. The immediate need is heat and power. The irony is severe. Humanity burns more fuel during a period of volcanic cooling. The added carbon dioxide does not overcome the short-term sulfate effect. The surface continues to cool. International climate politics are suspended but not erased. Scientists warn that when volcanic aerosols settle, greenhouse warming will return. Emergency emissions can create future consequences even when the present world feels frozen. Few leaders can think decades ahead while food supplies shrink by the week. Nia does not see Eli for 3 months. Travel from Oregon to Colorado is possible only through a chain of cleared rail lines and military transport. He chooses to remain in Portland because the city needs engineers and because leaving would consume space needed by evacuees from more dangerous valleys. The Cascade eruptions have changed. Some vents are quiet. Others continue producing ash and lava. Rain repeatedly remobilizes deposits into rivers. Communities near Mount Rainier and Mount Hood remain abandoned because lahars can continue long after explosive activity weakens. Portland is damaged but functioning. Its greatest advantage is organization. Neighborhood teams clear roofs, distribute water, repair filters, and check vulnerable residents. The city converts transit tunnels and underground parking areas into heated shelters. River transport resumes cautiously where channels remain open. Its greatest disadvantage is location. Ash keeps returning. Every dry wind lifts old deposits from streets and fields. A cloud can pass without a new eruption. Cleaning never feels complete. Eli begins working with a team designing intake systems that can be cleaned without shutting down entire buildings. The devices are simple, modular, and ugly. They save power. Nia watches him explain one design during a public video briefing. He looks thinner. She realizes he has become one of the experts people turn toward. He is still 22. At the end of the 3rd month, the first integrated global sulfur estimate is released. The amount injected into the stratosphere exceeds the Pinatubo eruption by many times, though direct comparison is difficult because emissions occurred at different latitudes, altitudes, and times. Aerosol layers now exist in both hemispheres. Some overlap. Some remain concentrated. Climate models converge around a peak average cooling of roughly 5 degrees Celsius during the first full year. Regional winter temperatures may fall far more. 5 degrees sounds small when spoken. The difference between the present climate and the coldest period of the last ice age was also measured in only several degrees globally. Human civilization is adapted to the narrow climate in which its farms, cities, reservoirs, and trade systems developed. A rapid 5-degree fall is not a cooler version of ordinary life. It is a new agricultural planet arriving within months. The public receives this explanation badly. Some people deny the models because their local afternoon remains warm. Others assume every place will freeze solid. Both misunderstand averages. A global mean combines tropical oceans, polar ice, continents, seasons, and nights. It does not describe one person's weather. A region can experience drought while the global average cools. Another can experience floods. A warm day does not cancel a planetary trend. The crisis teaches climate literacy through hunger. In the fourth month, major harvest reports arrive. North American grain production falls sharply. Europe loses large portions of several crops. Russia and Ukraine protect domestic reserves. China expands rationing and controlled environment agriculture. India struggles with disrupted monsoon rainfall and intense regional inequality. South American countries retain some productive zones, but face transport failures and ash from the Andes. Australia, distant from many land volcanoes, becomes one of the world's most important food exporters, though cooling, shipping limits, and domestic needs prevent it from feeding everyone. Parts of Africa experience mixed conditions. Some highland areas become dangerously cold. Some tropical zones maintain production, but lose imported fertilizer and machinery. East African volcanic regions face direct destruction, while Western regions become crucial agricultural corridors. No map divides the world cleanly into survivors and victims. A country may have food and no fuel. A country may have energy and no fertilizer. A country may have ports and no safe sea route. The global economy contracts beyond any previous measured crisis. Money still exists. It no longer guarantees delivery. Barter returns between governments at industrial scale. Grain for natural gas. Machine filters for medicine. Fertilizer for electricity. Shipping protection for food access. International institutions attempt to keep these exchanges transparent. Private networks and corruption grow around every shortage. Some people become rich during catastrophe. This is not new. The political danger rises with hunger. Governments impose curfews. Protests spread. Some regimes collapse. Others become more authoritarian and use emergency ration cards to punish opponents. Misinformation turns against scientists. NIA receives threats accusing volcanologists of hiding warnings, causing panic, exaggerating cooling, and working for foreign governments. The accusations contradict one another. Fear does not require consistency. She continues appearing in public briefings because familiar voices build trust. She explains what is known, what remains uncertain, and what actions matter. Wear proper respiratory protection in ash. Do not drive unless necessary. Protect water. Clear roofs safely. Follow local hazard maps. Expect cooling to last years, not forever. The last point becomes harder to communicate. For people who have lost homes, years are not temporary. For a child missing school, a year is enormous. For the stratosphere, a year is the time required for particles to begin settling. Scientific reassurance depends on scale. Human grief has its own. Near the end of month 5, Nia receives permission to travel west with an engineering convoy. The journey takes 9 days. She crosses plains under pale light, mountain passes cleared repeatedly, and towns where ash lies in drifts against buildings. In some places, the deposits are thin enough to sweep. In others, machinery pushes gray banks like winter snow. She reaches Portland after dark. Eli is waiting inside a converted transit station. They recognize each other immediately and still pause before embracing because both are wearing masks. When he removes his, Nia sees a scar near his forehead from falling roof material. He says it looks worse than it is. She says that is what people say when it looks exactly as bad as it is. For one night, they sleep in the same room beneath fluorescent emergency lights. Above them, ash begins falling again. By morning, Nia must return to Colorado. Eli remains. Their reunion lasts 11 hours. It is longer than many people receive. The first winter is approaching. The eruptions are no longer simultaneous in appearance. Some mountains have returned to silence. Some continue glowing. Some have collapsed into new craters. Some produce steam and gas from damaged systems. But the sunlight lost to all of them remains combined above the weather. The event has moved beyond geology. Humanity is entering the year without a normal summer anywhere. The first volcanic winter begins before the calendar says winter should have arrived. In October, snow falls across regions that normally expect it much later. In November, rivers freeze early. In December, cold records are broken across wide parts of the northern hemisphere. The southern hemisphere enters a damaged summer. Sunlight remains weak. Crops grow slowly. Frost reaches places where farmers did not plant for frost. Ocean winds shift. Rainfall arrives at the wrong time or not at all. Global average cooling reaches 4 degrees and continues downward. The phrase average again conceals the human experience. In Central Asia, nighttime temperatures fall more than 10 degrees below recent norms. In tropical cities, the change is smaller but still large enough to alter crops, insects, disease patterns, and energy demand. Some deserts receive unusual rain. Some forests dry. The atmosphere has not become uniformly cold. It has become unstable around a colder center. Food rationing moves from emergency policy to daily life. Adults receive calorie allocations based on work, health, pregnancy, and age. Children receive priority nutrients where systems remain fair. Black markets appear immediately. Families trade jewelry, electronics, tools, and property for grain. People learn the difference between hunger and starvation. Hunger is the body asking. Starvation is the body consuming itself. The world has enough stored food to prevent immediate universal famine, but reserves were never designed for several failed harvests and broken transport at the same time. Some countries prepared better. Some had strategic grain stocks. Some maintained public distribution networks. Some possessed cold-resistant agriculture or large fishing fleets. Others entered the crisis with conflict, debt, drought, or malnutrition already present. The eruption does not create equality through shared danger. It amplifies every inequality that existed before the sky changed. Humanitarian organizations face impossible choices. A shipment sent to one city cannot be sent to another. A convoy requires fuel, security, drivers, filters, spare tires, and roads that remain open. Food dropped from aircraft is rarely possible because safe flight corridors are limited and ash forecasts change rapidly. Ships become the backbone of international relief. The oceans remain navigable across many routes, though ports near erupting regions are damaged and volcanic ash threatens engines and crews. Naval vessels escort grain carriers. Floating pumice damages propellers. Harbors require constant dredging. A ship can carry far more food than an aircraft. It also takes weeks. People waiting at the destination live inside that difference. Fishing initially appears to offer an answer. The oceans contain enormous biological productivity. Yet fleets depend on fuel, refrigeration, safe ports, spare parts, and stable markets. Surface cooling and ash deposition change marine ecosystems. Some coastal fisheries improve temporarily where volcanic minerals stimulate plankton. Others collapse under acidification, darkness, contamination, or disrupted currents. Underwater eruptions cause severe local destruction. Hydrothermal systems change. Seafloor communities are buried or poisoned. Fish die near shallow vents. Coral reefs close to volcanic islands suffer from ash, heat, and sediment. The global ocean does not become sterile. Its volume is too great, its circulation too vast, and most eruptions too localized. Deep-sea organisms continue living in darkness as they did before. Life around hydrothermal vents survives conditions that would kill surface species. The ocean becomes a refuge from atmospheric temperature change and a victim of disrupted chemistry at the same time. This duality repeats everywhere. Ash destroys one field and eventually fertilizes another. Lava buries a forest and creates new land. Cooling kills crops and slows some heat-driven diseases. Nothing about the catastrophe is purely one thing. The overall balance remains devastating. In Portland, Winter turns ash into concrete like layers wherever drainage fails. Streets cleared in summer must be cleared again after storms wash material from roofs, hillsides, and parks. Lahars continue in river valleys around the Cascades. Fresh deposits remain loose. Rain remobilizes them. Communities dozens of kilometers from vents cannot return because the next flood may carry rock, trees, vehicles, and pieces of buildings through old channels. Eli moves from intake systems to water infrastructure. His team designs settling basins using parking lots and abandoned industrial land. Ash-laden water enters one side. Heavy particles sink. Cleaner water moves onward for treatment. The process is slow. The city needs slow. Fast pumps destroy themselves. Nia spends most of the winter in Colorado, where the emergency center has expanded into an international coordination campus. Tents and temporary buildings surround the original facility. Scientists, military planners, agronomists, engineers, doctors, economists, and translators work in shifts. Nobody planned the institution. The catastrophe assembled it. Every morning begins with the same four questions. How much sunlight reached the surface? Where did temperatures fall below crop thresholds? Which transport routes opened? How many days of food remain in each major region? Volcano activity appears fifth. This does not mean the eruptions have become unimportant. It means their largest consequence is now stored in the atmosphere. Nia's specialty shifts from magma to communication. She explains why some eruptions have stopped while cooling continues. She explains why falling ash can increase even after a local plume weakens, because old deposits are being lifted by wind. She explains why sulfur aerosols are not permanent. The last message is essential. The stratospheric veil will settle. Chemical reactions and circulation will remove it. The sky will brighten. No model suggests the planet will remain in volcanic winter forever. The question is what survives until then. During the coldest month, global average cooling reaches about 5 degrees Celsius. Some models predicted worse. Humanity is fortunate in one limited sense. Many eruptions released most of their material below the stratosphere, and several caldera systems produced smaller events than feared. The aerosol layer still blocks enough sunlight to collapse normal agriculture across much of the world. Fortune is a relative word. The first winter kills through cold, hunger, disease, and system failure. Hospitals ration electricity. Insulin and other temperature-sensitive medicines become difficult to distribute. Routine infections become deadly where antibiotics cannot arrive. Vaccination programs stop. Sanitation deteriorates in overcrowded shelters. Smoke from emergency heating worsens indoor air. Ash combines with dust and respiratory illness. The disaster creates no new pathogen. It weakens every defense against old ones. Governments count deaths differently. Some publish transparent estimates. Some hide them. Some lose the administrative capacity to count. There is no reliable global number. In this severe version of the scenario, the death toll by the end of the first year is measured in hundreds of millions. The larger threat remains ahead if food production does not recover. This is the point at which many fictional versions of the scenario end. The sky darkens. Civilization collapses. The story stops. Real catastrophe would not end so cleanly. People wake the next morning. They repair pumps. They argue over rations. They teach children inside shelters. They bury the dead. They improvise. Civilization is not one machine that switches off. It is millions of systems, some failing, some adapting, some becoming cruel, and some becoming more generous than before. The strongest adaptation comes from food science. Facilities once used to produce animal feed, fermentation products, and industrial microbes are converted to human nutrition. Bacteria, yeasts, fungi, and algae can create protein using less sunlight and land than traditional crops. The food is unfamiliar, processed, and culturally difficult for many people. It keeps people alive. Indoor farms prioritize potatoes, mushrooms, leafy greens, and seed crops. Artificial light is reserved for plants that provide essential vitamins or future planting material. Grain remains more efficient outdoors when any harvest is possible. Communities rediscover cold frames, root cellars, communal kitchens, and methods of preserving food that industrial abundance made less visible. Old technology and advanced biotechnology meet in the same ration. A meal may contain laboratory-grown protein, greenhouse spinach, stored wheat, and fermented vegetables prepared through a method thousands of years old. Seed banks distribute varieties bred for cold, short seasons, low light, and poor soil. Agronomists cross existing lines rapidly, sacrificing perfection for survival. Genetic engineering accelerates where laboratories retain power. New crops cannot be invented and deployed worldwide in one season, but research creates options for later years. Eli joins a project building insulated growing rooms beneath warehouses. Waste heat from generators and data centers warms water and soil. Carbon dioxide from fermentation is fed to plants. Every output becomes an input somewhere else. Efficiency once pursued for profit becomes a survival ethic. The project brings him to Colorado late in the first volcanic winter. He arrives thinner again, with gray ash permanently embedded in the seams of his backpack. Nia meets him outside the operations center. This time, they embrace before removing their masks. He tells her Portland is still there. She tells him the sun is returning. The statement is technically true. Instruments show slightly more light reaching the surface than 3 months earlier. No human eye can yet see the difference. They celebrate anyway. That night, Nia and Eli eat together in the campus kitchen. Their meal is mushroom protein, potatoes, preserved cabbage, and a square of chocolate divided among 6 people. The chocolate came from a warehouse stock held since before the eruptions. Nobody knows when cacao will be available again. The square tastes more intense than anything Nia remembers. Scarcity changes flavor. Outside, snow falls through air, still carrying fine ash. Inside the stratosphere, invisible particles continue settling one fraction at a time. The catastrophe has reached its darkest season. The planet has already begun the slow physical process of leaving it. The second year begins with fewer eruptions and more consequences. Most volcanoes have returned to lower activity. Some continue releasing lava or gas. A smaller number remain explosively active. Several submarine systems continue building new seafloor. Fresh domes grow inside craters and collapse. Rain repeatedly remobilizes ash into lahars. The phrase, "every volcano erupted," is now historical. The landscape remains in the present tense. In satellite images, coastlines have changed around several islands. New lava deltas extend into the sea. Caldera collapses have created bays. Landslides have blocked valleys and formed unstable lakes. Rivers follow new channels across deposits. Maps become outdated faster than they can be printed. Survey teams return cautiously to damaged regions. Drones fly where aircraft cannot. Radar penetrates clouds. Satellites measure ground deformation, heat, and gas. Scientists begin separating the original synchronized event from the ordinary volcanic processes that followed it. They make an important discovery. The impossible trigger did not permanently connect Earth's magma systems. Once the initial eruptions began, each volcano returned to behaving locally. One continued because deeper magma rose. Another stopped because pressure fell. A third changed vent. A fourth entered collapse. The planet did not acquire a new global volcanic rhythm. The synchronization happened once. This matters for hope. There will not be another simultaneous pulse simply because the first occurred. In the real world, even the first has no mechanism at all. Nia says this during the anniversary briefing. She avoids the phrase 1 year since because people experience the date differently. For families near volcanoes, the catastrophe began with sound and heat. For distant cities, it began when food stopped arriving. For farmers, it began with frost. For children born during the crisis, it has always existed. The anniversary produces ceremonies and protests. Some governments honor rescue workers. Some citizens accuse leaders of wasting reserves before the disaster. Some communities refuse public mourning because they are still searching for missing people. A global event does not create one global memory. The second year's most important scientific question concerns sunlight. Aerosol measurements show clear decline. The stratosphere remains hazy, but the thickest concentrations have begun dispersing and settling. Average temperatures are still far below the old climate, yet the cooling no longer deepens. The world has reached the bottom. Climbing out will take longer than falling in. The second growing season is planned around this knowledge. Agricultural zones shift toward lower latitudes and lower elevations where possible. Fields once devoted to export crops are converted to staples. Governments subsidize cold-tolerant grains, potatoes, legumes, and protected cultivation. The international grain agreement created during the first year becomes permanent. Countries contribute a share of production to a common emergency pool in exchange for guaranteed access during regional failure. The system is imperfect. Shipments are stolen. Governments underreport harvests. Powerful countries receive more than poor ones. It still moves enough food to prevent several famines from becoming larger. Humanity survives not through one invention, but through thousands of partial successes. A railway repaired 2 weeks early. A reservoir protected from ash. A fungal protein factory kept powered. A farmer planting the wrong crop at the right time. A local official refusing to divert rations. A ship captain entering a damaged port. A technician cleaning one filter before it fails. Disaster statistics flatten these acts into numbers. People experience them as days added to life. Eli moves permanently to Colorado to work on resilient food and water systems. Portland no longer requires every volunteer, and the National Coordination Center has become a place where designs can spread. He dislikes leaving. Nia reminds him that leaving a city is not abandoning it if the work returns. Together, they help create open engineering manuals translated into dozens of languages. The plans use components available in ordinary hardware systems whenever possible. Settling tanks, washable filters, reinforced greenhouse roofs, low-pressure irrigation, waste heat recovery, and ash-resistant ventilation are shared without patents. Private companies object. Emergency governments ignore them. The crisis changes ideas about ownership. A design capable of protecting water cannot remain proprietary while cities are thirsty. This principle will be challenged later when normal markets return. For now, survival wins. The second year also reveals ecological damage that was invisible during the first. Mountain forests near explosive vents are gone. River systems are buried beneath sediment. Ash has smothered grasslands and wetlands. Acidic deposition damaged leaves and freshwater ecosystems. Cold killed species unable to migrate or reproduce quickly. Island species with small ranges disappear entirely. The extinction toll is not comparable to the greatest mass extinctions in Earth's history. It is still one of the most rapid ecological losses humans have witnessed. The event does not sterilize the biosphere. It rearranges it violently. Some species expand. Cold-tolerant plants move into lower regions. Scavengers thrive where animals died. Insects decline in one place and multiply in another. Ocean plankton blooms after ash delivers iron to nutrient-poor waters, then collapse when chemistry and light shift again. Ecologists resist describing recovery as a return. A new ecosystem is not the old one repaired. It is a different community growing from what survived. Around Mount St. Helens, scientists once learned that life returned through protected pockets, surviving roots, burrowing animals, drifting seeds, and waterways. The simultaneous eruption creates this process across thousands of landscapes. At first, the recovering land looks empty. Then color appears. Algae grow on wet ash. Moss takes hold. Insects arrive. Birds carry seed. Grasses emerge where sunlight and temperature allow. The first green shoots become international symbols. They are used in political speeches, advertisements, religious ceremonies, and fundraising campaigns. The plants do not know they are symbols. They are simply alive. Volcanic regions also become dangerous again during rain. Ash deposits can remain unstable for years or decades. Lahars follow river valleys long after the sky clears. People returning home must learn that the end of eruption is not the end of hazard. Rebuilding cannot follow the old map blindly. Some towns are relocated to higher ground. Some roads are abandoned. Some valleys become permanent exclusion zones. This creates conflict. Land is memory, inheritance, identity, and wealth. A hazard map can tell a family that the place containing generations of history should never be occupied again. Scientific accuracy does not make the loss easier. Eli visits Oregon to help design a relocated water system for communities near Mount Hood. Residents accuse planners of using disaster to remove them from valuable land. Some accusations are justified. Developers are already seeking access to safer zones. Recovery creates profit opportunities before grief has ended. Public land trusts are established in several regions to prevent forced sales. Residents receive ownership shares in rebuilt towns. The policies work unevenly. No disaster automatically produces justice. It creates moments when systems can be changed. People decide how. In the second winter, temperatures remain several degrees below the old average, but the decline has stopped. Daylight is stronger. Solar generation improves. Protected agriculture expands. The global food deficit remains severe, yet production rises for the first time since the event. This improvement creates its own danger. Governments consider ending rationing too early. Markets anticipate recovery and raise prices. People exhausted by emergency rules demand freedom. Scientists warn that one better harvest does not mean stability. The aerosol layer could persist another year or more. Weather remains altered. Seed reserves are limited. Infrastructure is fragile. A political movement emerges around the phrase "the sky is clear." Its supporters argue that experts are extending crisis powers after the danger has passed. They point to blue days and recovering markets. Some are genuinely concerned about authoritarian government. Others profit from deregulation. Nia appears before an international assembly and says that the sky can look clear while the stratosphere still contains enough aerosol to alter climate. A delegate asks whether she is asking citizens to trust instruments over their own eyes. She answers yes. The statement is used against her. Science often asks people to accept measurements beyond direct perception. Carbon dioxide has no color. Radiation may have no smell. A global temperature average cannot be felt in one afternoon. Trust depends not only on data, but on whether institutions have been honest before. Several governments have not. The debate becomes less about volcanoes than legitimacy. Emergency powers begin expiring in democratic states. Courts review ration systems and movement restrictions. Some authoritarian governments keep controls permanently. The catastrophe does not unite the world into one political future. It pushes societies along directions already present. Some become more cooperative. Some become more fearful. Some build stronger public institutions. Some build stronger surveillance. The shared sky contains different choices beneath it. Near the end of year 2, Eli finds Nia asleep at her desk. She has spent months telling the public that rest and judgment matter during crisis, while ignoring both herself. He covers her with a coat and turns off one monitor. The screen shows global temperature anomaly. The line is still far below zero. It is moving upward. For the first time, The direction matters more than the distance. Outside, dawn arrives through a thinner haze. Buildings cast shadows with sharper edges. People notice before the instruments announce it. The sun has begun to look like the sun again. During the third year, the world relearns brightness. The change is gradual enough that people argue about when it began. Some remember the first morning when a shadow looked sharp. Some remember solar panels producing more power. Some remember removing a lamp from an indoor farm because the plants no longer needed it all day. Children notice colors returning to the sky. Adults notice ration portions increasing. The global average temperature remains far below the climate before the eruptions, but each season becomes less abnormal than the one before. Aerosols continue settling from the stratosphere. Rain and atmospheric circulation remove lower particles. The most persistent eruptions release too little sulfur at too low an altitude to replace what is being lost. The volcanic winter is ending. It does not end on one date. Tropical agriculture recovers first in several regions. Temperate zones follow unevenly. Ocean temperatures lag behind the atmosphere. Snow and ice accumulated during the cold years melt slowly, affecting rivers and sea level in complex ways. The first successful global grain harvest is celebrated like the end of a war. It is still smaller than harvests before the catastrophe. Celebration does not require completeness. Rationing remains for another year. Then some countries end it. Others continue because domestic production has not recovered. Food aid shifts from universal emergency to long-term rebuilding. The world population is smaller. No precise number can describe the loss with confidence. Records failed in the regions where deaths were greatest. Migration blurred census systems. Some governments hid famine. Some communities disappeared from communication and later returned. Historians will argue over the total for generations. The number matters. So do the lives hidden inside uncertainty. Every city contains empty apartments. Every school contains missing names. Every family measures the catastrophe differently. NIA's operations center changes again. The emergency campus becomes the International Earth Recovery Institute. Temporary tents are replaced by permanent laboratories. The original volcano room is preserved with its old screens, partly as history and partly because several volcanoes remain active. Nia is asked to become director. She refuses at first. She wants to return to field science, to one mountain, one set of instruments, one problem small enough to understand deeply. Eli asks whether that desire is real or whether she is tired of making decisions that affect people she cannot see. Both. She accepts the position for 5 years. The Institute studies more than recovery. It studies failure. Why did one city retain water while another lost it? Why did one food network distribute fairly while another collapse into violence? Why did some hospitals function with half their normal power? Why did some evacuation plans kill people by directing them onto dangerous roads? Engineering reports include social trust, local knowledge, disability access, language, and governance beside concrete, filters, fuel, and storage. The catastrophe demonstrated that infrastructure is not only physical. A warning nobody trusts is failed infrastructure. A shelter people cannot reach is failed infrastructure. A grain reserve controlled by corruption is failed infrastructure. The rebuilt world begins designing systems around this broader definition. Not everywhere. In some regions, reconstruction restores the same vulnerabilities because speed and profit dominate planning. Cheap roofs return to ash zones. Settlements expand into lahar valleys. Food reserves are sold when prices rise. Emergency budgets shrink as memory fades. Human beings are capable of learning. They are also capable of deciding that a lesson is inconvenient. Eli travels constantly, helping cities adapt water systems and controlled agriculture. He returns to Portland each year. The city has changed beyond the damage. Some neighborhoods were abandoned because ash removal and landslide risk made rebuilding too expensive. New districts grew around protected transit, water storage, and indoor farms. Roofs are steeper. Air systems contain washable volcanic filters as standard equipment. Mount Hood remains on the horizon. Its shape is altered. The mountain is quieter, not harmless. People hike on reopened trails outside exclusion zones. Children born after the eruption learn evacuation routes before they learn the names of every peak. Life near volcanoes continues because life near volcanoes always continued. The difference is memory. In the fourth year, Nia and Eli visit a valley near Mount Rainier that remains closed to permanent settlement. The old town is buried beneath layers of lahar sediment. Only the upper section of a church tower remains visible. Eli asks whether the town should be excavated. Nia says archaeology and grief may answer differently. The government plans to leave much of it untouched as a memorial and hazard reserve. Survivors disagree. Some want homes recovered. Some want the dead left in peace. Some want no tourist site built from loss. There is no solution that satisfies everyone. The valley becomes a place where warning sirens are tested every month, even though nobody lives there. Sound travels through empty streets. Farther south, volcanic landscapes begin attracting visitors again. Tourism returns first through scientists, journalists, and relatives. Later come travelers who want to see new craters, islands, lava fields, and forests growing through ash. Local communities set limits. Disaster sites are not theme parks. Yet visitors bring money needed for rebuilding. The same tension existed before the event and becomes stronger after it. People are drawn toward the places that frighten them. Seeing a cooled lava flow can make catastrophe feel bounded. Touching new rock can make geological time feel physical. The oceans reveal their recovery more slowly. Pumice rafts carry organisms across great distances. New hydrothermal vents support microbial life. Some fisheries return. Others reorganize around different species as temperatures and nutrients shift. Marine scientists discover several new islands created by submarine and island arc eruptions. Some erode within years. Others remain above water long enough for birds to land and plants to establish. Nations argue over whether new land changes maritime boundaries. The planet creates rock. Law immediately asks who owns it. International courts decide that uninhabited volcanic islands formed during the event cannot extend exclusive resource zones for 25 years. The pause allows scientific study and prevents the fastest naval power from claiming every new surface. The agreement is praised as enlightened. It was reached only after several dangerous confrontations. By year 5, global temperature has returned close to the trajectory expected before the eruption. This produces a psychological shock. Many people assumed the volcanic winter had solved global warming. It did not. Sulfate aerosols reflected sunlight temporarily. They did not remove most carbon dioxide already accumulated in the atmosphere. As the veil clears, greenhouse warming reappears beneath it. The emergency burning of fossil fuels added more emissions. The rebuilt world faces an old crisis after surviving a new one. Some citizens refuse to accept another demand for sacrifice. They spent years cold and hungry. They do not want to hear that the planet may now become too warm. Climate scientists explain that cooling and warming can come from different causes at different times. The public hears contradiction. Politics turns the atmosphere into opposing memories. One generation remembers cold as the enemy. Another remembers heat. The Earth can contain both. The catastrophe accelerates energy transition in an unexpected way. Resilient grids built during the dark years already combine nuclear, geothermal, wind, storage, controlled demand, and regional microgrids. Solar power returns strongly as skies clear. Indoor agriculture becomes more efficient and less energy-intensive when natural light improves. Emergency systems become ordinary climate infrastructure. Not because humanity planned perfectly, because equipment built for one crisis can serve another. The first pre-eruption style summer arrives in year 6. It is warm, bright, and emotionally difficult. People gather outdoors after years of filtered interiors. Festivals return. Crops flower under full light. Children complain about heat. Nia stands in a field outside the Recovery Institute, while agronomists examine wheat bred from varieties selected during the volcanic winter. The plants tolerate cold, short seasons, and low light. Under the restored sun, they grow exceptionally well. A catastrophe has changed the crop without intending to. Eli pulls one head of grain between his fingers. He says it looks ordinary. Nia tells him that ordinary is often the most expensive thing to rebuild. By year 8, food production exceeds the needs of the reduced global population. Famine ends as a worldwide condition, though local hunger remains through poverty and conflict. By year 10, most atmospheric sulfate from the synchronized eruptions is gone. Ash remains in soil, buildings, lungs, archives, and memory. Lahars still occur after heavy rain. Some exclusion zones remain permanent. Some volcanoes erupt again through ordinary local processes. Each new eruption creates fear far beyond its actual hazard. A single plume appears on global news, and people remember the morning when every dot turned red. Nia returns to public briefings one more time. She says the new eruption is serious for nearby communities and not connected to volcanoes elsewhere. A journalist asks whether she is certain the simultaneous event cannot happen again. She answers that it had no physical mechanism the first time. That is the strange privilege of a thought experiment. It can happen once because the story allows it. The real Earth remains governed by geology. Volcanoes are separate. The planet is active. The impossible morning is not waiting beneath the next sunrise. 25 years after the eruptions, the event has acquired a name. People call it the convergence. Scientists dislike the word because it suggests volcanic systems physically came together. Historians keep it because language follows memory more often than mechanism. Nia is 71 when the International Earth Recovery Institute opens a permanent exhibition about the first day. The room contains the original global alert map, a section of collapsed roof, a damaged aircraft engine, an ash-covered water filter, ration cards, seed packets, and the message Eli sent from Portland. I am inside, breathing okay. He gave permission for the message to be displayed and regrets it immediately. Visitors treat 4 frightened words as a statement of courage. He says he was not courageous. He was reporting facts. Nia tells him that courage often looks like continuing to report facts. Eli is now a water and food systems engineer with gray in his hair. He helped design infrastructure standards used across volcanic and non-volcanic regions. His most important work is not one machine. It is a rule requiring cities to maintain several independent ways to provide drinking water. The rule costs money during normal years. It saves lives during earthquakes, fires, cyber attacks, droughts, and ordinary equipment failure. Many lessons of the convergence spread beyond volcanoes. Food reserves are rotated rather than stored until they spoil. Critical filters and machine parts are manufactured in several regions. Power grids can separate into smaller functioning islands. Hospitals keep longer supplies of essential medicine. Emergency warnings include people without cars, people with disabilities, migrants, prisoners, and communities speaking minority languages. Not every place follows the standards. The world is safer than before in some ways and more damaged in others. Entire ecosystems vanished. Several island cultures lost most of their homeland. Volcanic landscapes once supporting dense communities remain exclusion zones. Political states collapsed during famine. Borders changed under migration pressure and conflict. The number of people alive is far lower than it would have been without the event. Recovery is not reversal. A repaired world is not the untouched world returned. The climate has also resumed warming. The cold interval appears in temperature records as a deep temporary valley. Researchers use it to understand aerosols, clouds, ocean heat, and agricultural vulnerability. The data are scientifically extraordinary. No scientist wishes the experiment had occurred. This distinction matters whenever knowledge comes from disaster. Useful evidence does not justify suffering. Nia spends her final years studying how the first sulfur estimates were communicated. She concludes that the science was more accurate than the public memory suggests and less complete than the scientists believed at the time. Some warnings were too cautious. Some were too confident. Some uncertainty ranges were interpreted as indecision. Some simple messages concealed important differences. Her final report recommends that future crisis communication begin with 3 statements. What we know, what we do not know, what action remains sensible under both. The method is adopted by emergency agencies beyond volcanology. Eli reads the report after her death. The final page contains no mention of him. Inside the physical copy, he finds a handwritten note. You were inside. You kept breathing. Then you helped other people do the same. He places the note beside the original message in the exhibition, but asks that it remain folded. Not every part of history needs to become public. By then, the world has developed a clearer understanding of what the simultaneous eruptions did and did not do. They did not empty Earth's mantle. Magma is not one ocean immediately beneath the crust. The mantle is mostly solid rock that moves slowly over geological time. Eruptible magma forms in limited regions and collects in complex systems. Even thousands of eruptions release only a tiny fraction of Earth's interior. They did not stop plate tectonics. Plates continue moving at rates measured in centimeters per year. Subduction continues. Mid-ocean ridges create crust. Mountains rise and erode. Future volcanoes form. They did not use up volcanism. A volcano can erupt again when magma accumulates and pressure builds. New systems may develop across millions of years. They did not cover the entire planet in lava. Even enormous lava flows occupy limited regions compared with Earth's surface. Most people were never physically near molten rock. They did not keep the sky dark forever. Ash fell quickly compared with sulfate aerosols. Sulfate remained for years, then declined. The volcanic winter ended because the atmosphere removes particles even when human beings cannot accelerate the process easily. They did not produce one universal tsunami. Many regional waves occurred through explosions, collapses, and landslides. Their effects depended on water depth, displaced volume, coastline shape, and distance. They did not kill all life. Deep oceans, underground ecosystems, seeds, roots, microbes, insects, animals, and protected habitats survived. Life expanded from countless refuges. They did not end humanity. They came close to breaking the systems that support billions of people. The survival of civilization depended less on escaping lava than on maintaining calories, water, heat, medicine, information, and social cooperation. This becomes the central lesson taught in schools. Catastrophe is often indirect. The thing seen on the screen is not always the thing that causes the greatest loss. A volcano erupts. Ash closes a road. The road prevents fuel delivery. The fuel shortage stops a pump. The pump failure contaminates water. The water failure closes a hospital. The chain can be interrupted at many points. Resilience means creating more points where interruption is possible. Children study the event through family histories. One interviews a grandmother who spent 2 winters inside an underground farm. Another speaks with a fisherman who navigated pumice-filled water. Another records a refugee whose island became uninhabitable. Another has no family story because records were lost. The absence becomes part of the archive. The convergence also changes religion and philosophy. Some people interpret survival as divine protection. Some interpret the catastrophe as evidence of a universe indifferent to human life. Some traditions create days of fasting and shared food. Others reject any attempt to give the event meaning. The eruptions provide no answer. Geology describes processes. Meaning remains human work. Art from the decades after the event repeatedly uses three images: a red map, a pale Sunday, a green shoot in ash. The images move from direct memory into symbols. People born long afterward use them without feeling the fear that created them. This is how catastrophe becomes culture. The final eruptive episode, still traceable to the original synchronized moment, ends 37 years after the first day. It occurs along a remote island arc and remains mostly submarine. Scientists debate whether it belongs to one extraordinarily long eruption or to a chain of closely connected episodes. The distinction matters to databases. To the public, it means the convergence is officially over. No ceremony is planned. A small research vessel lowers an instrument through calm water. The final thermal signal has returned to background. The team records the time. The youngest scientist aboard was born 16 years after the first day. She looks across the sea and says she expected something to happen. Nothing does. The ocean moves. Clouds cross the sky. The planet does not recognize the end of a historical category. The scientist closes the data file. Far below, heat continues moving through rock. Elsewhere, dozens of ordinary volcanoes remain in ordinary eruption, as volcanoes do on a living geological planet. The impossible simultaneity has ended. Volcanism has not. The Earth is not quiet. It is normal. The generation born after the convergence inherits an unusual relationship with mountains. Children learn that volcanoes are not sleeping monsters and not harmless scenery. They are geological systems with histories, warning signs, and uncertainties. Schools near active regions practice evacuation without presenting eruption as inevitable. Hazard maps become as ordinary as fire exits. Global monitoring changes permanently. Before the event, many volcanoes had limited instruments or none at all. Wealthier countries maintained dense networks, while remote systems were known mainly through satellites and occasional field surveys. Afterward, governments fund a shared observing system designed around the idea that data from one region benefits every region. Seismometers, gas sensors, ground deformation instruments, satellites, infrasound stations, ocean pressure sensors, and local observers contribute to one distributed archive. The archive does not predict every eruption. No instrument can promise certainty. It improves the time between warning and impact, and sometimes time is the entire difference between a tragedy and an evacuation. The network also changes who counts as an expert. Scientists bring models and instruments. Residents bring generations of experience with rivers, animals, weather, roads, and the behavior of particular slopes. Indigenous knowledge is recorded with permission rather than extracted and renamed. Emergency plans are tested by the people expected to use them. The most successful observatories become relationships rather than buildings. Communities know the scientists. Scientists know which warnings will be heard. This trust becomes one of the quieter legacies of the catastrophe. The Convergence Memorial does not list volcanoes by size. It lists places and people. A small eruption beside a town may have caused more immediate loss than a powerful eruption in an uninhabited region. A distant city may have lost thousands through water failure without receiving measurable ash. The memorial resists the human habit of ranking disaster only by spectacle. In its central hall, visitors stand beneath a model of the atmosphere. Tiny lights show how sulfur spread from separate plumes and became one planetary veil. Below it, another display shows the systems that kept people alive. A pump, a seed, a filter, a radio, a ration card, a ship's route. The objects look too ordinary for a disaster museum. That is the point. The final display contains a simple statement. The mountains erupted separately. The consequences connected them. Visitors leave through a garden planted in soil mixed with volcanic ash from several continents. The plants were chosen not because they are exotic, but because they are common food crops. Wheat, beans, potatoes, cabbage. The garden is harvested each year and served in a community kitchen. Memory becomes calories again. Long after the event, geologists drill into deposits and read the synchronized year as a marker across the planet. Ice cores contain sulfate. Lake beds contain ash. Tree rings narrow. Marine sediments record changes in plankton and erosion. Future scientists will identify the layer even if every digital archive disappears. The Earth writes catastrophe into material. It does not write the meaning. That remains in stories, laws, rebuilt towns, changed crops, and the decisions people make when another local volcano shows unrest. The planet returns to ordinary volcanism. Humanity does not return to ordinary forgetfulness so quickly. What, then, would actually happen if every volcano on Earth erupted at the same time? The first answer is that the scenario needs a definition before it can have a scientific result. Earth contains old volcanic mountains whose magma sources ended millions of years ago, active vents erupting now, dormant systems capable of waking again, large calderas, volcanic fields, fissures, and countless features beneath the oceans. There is no exact number agreed upon because the word volcano can describe a cone, a vent, a field, or a connected magma system. In the meaningful version of this thought experiment, every active or potentially active system with a current source of magma begins erupting simultaneously. Extinct volcanic remnants remain rock. The second answer is that every eruption would not have the same size or character. Most volcanoes are not supervolcanoes. Most would not produce continent-scale explosions. Shield volcanoes would tend toward lava flows and fountains. Many submarine eruptions would be limited by water pressure. Stratovolcanoes could produce explosive ash columns, pyroclastic flows, landslides, and lahars. Caldera systems could produce major eruptions without automatically repeating the greatest events in their history. The total catastrophe comes from simultaneity, not from turning each volcano into the largest eruption physically imaginable. The third answer is that the direct destruction would be severe and regional rather than one uniform wave across Earth. Communities beside explosive volcanoes would face the highest immediate mortality. Pyroclastic flows could destroy almost everything in valleys and on volcanic slopes. Lahars could travel far downstream, especially from snow-covered volcanoes or systems with crater lakes. Lava would bury roads, buildings, and farmland. Gas would threaten low areas and communities downwind. Many people living far from volcanoes would survive the first hours without seeing lava or feeling a damaging earthquake. The disaster would reach them through ash, transport, food, energy, and climate. The fourth answer is that most long-distance commercial aviation would halt or become severely restricted almost immediately. Volcanic ash can abrade aircraft, contaminate instruments, and melt inside jet engines. With explosive plumes rising across most volcanic regions, safe routes and alternate airports would disappear faster than aviation authorities could recalculate them. Aircraft already flying would attempt to land. Many would succeed. Some would encounter ash because no global system has ever managed thousands of overlapping clouds. The loss of aviation would affect more than travel. Medical supplies, emergency personnel, machine parts, fresh food, and high-value cargo often move by air. The world would lose speed at the moment it needed speed most. The fifth answer is that ash would become the most widespread immediate hazard. Lava is visually dramatic and geographically limited. Fine ash can travel enormous distances. Even a few millimeters can damage machinery, contaminate water, reduce visibility, harm crops, disrupt power, close roads, and interfere with communications. Wet ash becomes much heavier, and can collapse roofs. Ash would not fall equally everywhere. Winds and plume height would decide which regions received thick deposits. Some continental interiors might remain relatively clear during the first days. Other regions would receive repeated layers from several volcanoes. Cleaning would continue for years because wind can lift deposits after eruptions stop. The sixth answer is that the oceans would not boil and the planet would not explode. Most submarine volcanic activity occurs under pressures that limit explosive gas expansion. Deep eruptions would create lava, heat, chemical changes, and local ecological damage without throwing enormous plumes into the atmosphere. Shallow eruptions, volcanic flank collapses, and submarine landslides could produce regional tsunamis. There would be many sources, not one universal wall of water. Earth's crust would remain intact. Plate tectonics would continue. The event would release an enormous amount of energy by human standards and a small amount compared with the energy contained inside the planet. The seventh answer is that sulfur, not visible ash, would create the longest global atmospheric crisis. Most ash falls from the atmosphere in days or weeks. Sulfur dioxide reaching the stratosphere can form sulfate aerosols that reflect sunlight. These particles can spread around the planet and remain for years. One major eruption can cool global climate measurably. Many major eruptions in both hemispheres could produce several degrees of rapid cooling. The exact value cannot be calculated without choosing the size, sulfur content, latitude, season, and plume height of every eruption. Their effects would not add in a simple straight line. A scientifically cautious scenario still produces a severe volcanic winter. The eighth answer is that global average cooling would not mean identical cold everywhere. Continents would cool faster than oceans. Some regions would become colder and drier. Rain belts and monsoons could shift. Storm tracks would change. Tropical agriculture could fail through reduced light and rainfall, even without freezing temperatures. A global average fall of several degrees would represent an enormous climate shock because farms and water systems are adapted to recent local seasons. The world would experience unusual frost, short growing seasons, crop failures, weak sunlight, and unstable rainfall at the same time. The ninth answer is that famine would become the greatest long-term threat. The planet would still contain food after the eruptions. The problem would be protecting, moving, and replacing it. Ash would damage fields and machinery. Fuel and fertilizer deliveries would stop. Electricity failures would spoil cold storage. Countries would restrict exports. Transport routes would close. Several growing seasons could fail before sunlight recovered. Billions of people depend on global food systems that assume predictable weather and continuous trade. The catastrophe would attack both assumptions. The death toll could not be estimated honestly from the title alone. It would depend on eruption magnitude, season, food reserves, political decisions, infrastructure, and how quickly controlled agriculture expanded. A severe scenario could kill hundreds of millions and place billions at risk. Human extinction would remain unlikely because populations, food stores, energy systems, climates, and distances from volcanoes are widely distributed. Survival would not mean avoiding immense loss. The 10th answer is that artificial food production and protected agriculture would become essential. Indoor farms could not instantly replace global fields. They require electricity, equipment, nutrients, and time. They could produce vegetables, seed stock, and some staple crops. Fungi, algae, yeast, and bacteria could create protein with limited sunlight and land. Greenhouses, root crops, cold-tolerant grains, communal kitchens, and food preservation would all matter. The solution would combine advanced biotechnology with old agricultural knowledge. No one technology would feed everyone. Thousands of systems would each prevent part of the famine. The 11th answer is that energy diversity would determine which regions adapted best. Solar generation would fall under ash and aerosol haze. Hydroelectric systems could suffer abrasion and sediment. Thermal plants would need protected air intakes. Geothermal facilities might be damaged by nearby eruptions. Wind turbines would require maintenance. Nuclear plants would need secure cooling, staff, filters, and spare parts. Regions depending entirely on one system would be vulnerable. Regions able to separate into local microgrids and combine several sources would keep hospitals, pumps, heating, communications, and indoor food production operating longer. The catastrophe would reward redundancy that looked inefficient before it was needed. The 12th answer is that real volcanic hazards would continue after visible eruptions ended. Rain can remobilize ash and rock into lahars years or decades later. Rivers can flood through sediment. Slopes can collapse. Ash can return to the air during dry weather. Water systems can remain contaminated or damaged. A community might survive the eruption and remain unable to return home. Reconstruction would require moving some settlements rather than rebuilding every road and house in the same place. This would create conflict between safety, property, memory, and justice. The 13th answer is that the volcanic winter would end. Sulfate aerosols do not remain in the stratosphere forever. They settle and are removed through atmospheric processes. Depending on the total injection and continued eruptions, the strongest cooling could last several years, followed by gradual recovery. Sunlight would return. Agriculture would expand. The climate would move back toward the conditions determined by greenhouse gases and natural variability. The eruption would not reset Earth permanently into an ice age unless additional feedbacks and conditions far beyond the original premise were added. The 14th answer is that volcanic carbon dioxide would not necessarily become the main immediate climate effect. Large eruptions emit carbon dioxide, but sulfur-driven cooling dominates the first years when strong explosive plumes reach the stratosphere. A single synchronized episode would not automatically create the prolonged greenhouse gas release associated with flood basalt events lasting thousands or hundreds of thousands of years. The long-term climate could return to warming after aerosols cleared. The world might emerge from volcanic winter with more atmospheric carbon dioxide from emergency fuel use and damaged climate policy. One crisis would not solve another. The 15th answer is that ecosystems would be devastated without disappearing. Life would survive in deep oceans, underground habitats, sheltered valleys, seeds, roots, microbial communities, and regions receiving limited ash. Pioneer species would colonize deposits. Rivers and forests would reorganize. New volcanic land would appear. Some species with small ranges would become extinct. Some ecosystems would never return in their old form. Recovery means life expanding again, not every lost species reappearing. The 16th answer is that international cooperation would be necessary and incomplete. No country could manufacture every filter, medicine, seed, fuel, and machine part it needed. Food and energy would have to cross borders. Scientific data would need to be shared. Ships and railways would become strategic lifelines. Governments would also hoard supplies, hide losses, and use emergency powers. Some communities would cooperate remarkably. Others would experience corruption, violence, and authoritarian control. A common catastrophe would not create one common human response. The 17th answer is that the event would transform science. Satellites, ice cores, atmospheric instruments, ocean sensors, and ecological surveys would produce unprecedented data. Researchers would learn about volcanic aerosols, climate sensitivity, food vulnerability, ecosystem succession, and the behavior of many poorly studied volcanoes. The knowledge would be valuable. It would not make the catastrophe worth experiencing. Science can learn from suffering without treating suffering as an experiment anyone would choose. The 18th answer is that the modern world would survive in pieces before reconnecting. The internet would continue through some cables and data centers. Power grids would separate. Cities would become more dependent on local water, local energy, and local food. National governments might weaken while municipalities and regional networks kept people alive. Civilization would not switch off everywhere at once. It would become fragmented, slower, poorer, and more local. Reconnection would take years. The final answer is that the image of every volcano erupting is not primarily a story about lava. It is a story about sunlight and systems. The immediate spectacle would be mountains exploding, fissures glowing, ash lightning, and red maps. The lasting danger would be quieter. A dimmer noon, a failed harvest, a clogged pump, an empty pharmacy, a road no truck can use, a treaty deciding whether grain crosses a border. Humanity would survive by protecting the ordinary systems that stand between geological violence and a human body. Clean air, safe water, warmth, calories, medicine, information, trust. The volcanoes would begin the disaster in one impossible moment. The future would depend on what people did during every ordinary moment that followed. Return now to the first night, before the years of cold, rebuilding, and memory. Nia is sitting beside a window in the Colorado Operations Center. The glass is designed to resist storms. Tonight it holds back fine ash drifting from eruptions more than 1,000 kilometers away. The parking lot lights create pale cones in the haze. Each particle falls separately. Together they soften the world. Inside, machines continue measuring the catastrophe. A printer releases maps that become outdated before the paper cools. Radios carry voices from observatories losing power. Satellite images arrive in layers. Emergency coordinators speak several languages across one channel, then fall silent while translation catches up. Nia has been awake for 23 hours. Eli's last message remains open on her phone. Building holding. The words are not enough to tell her whether he is safe. They are enough to let her breathe for another minute. A younger scientist named Tomas sits beside her. He began working at the center 8 months earlier. Until tonight, his largest emergency involved a restless volcano that never erupted. He asks whether the cooling models can be wrong. Nia says yes. He asks whether they could be too severe. Yes. He asks whether they could be too mild. Yes. Tomas looks toward the screens and says that uncertainty seems useless. Nia tells him uncertainty is not the absence of knowledge. It is the boundary around what knowledge can honestly claim. Inside that boundary, people can still act. They know ash will damage engines. They know sulfur in the stratosphere will reduce sunlight. They know food and water must be protected. They know every save day matters. They do not need the exact temperature of next year's July afternoon before moving grain into secure storage tonight. Tomas returns to his desk. Nia remains by the window. Imagine sitting there with her for a moment. Not inside the fear, only inside the scale. Beyond the dark glass, Earth continues turning. The Colorado mountains move toward sunrise. Portland remains beneath ash. Across the Pacific, another region enters evening. Some volcanoes are producing lava that glows against darkness. Some are hidden inside storms. Some undersea vents are building rock where no human eye will ever see it. The planet is active in thousands of places. It is also still mostly quiet by area. Fields lie between volcanic ranges. Deserts stretch beneath altered skies. Oceans move around continents. People wait in rooms. The event is global without every place looking the same. This is often how large changes exist. A line on a graph can represent millions of separate mornings. A global average can contain one family freezing, another fleeing rain, and another watching crops fail under a warm sky. The mind wants one image. Reality keeps many. Follow the ash upward. Near the ground, coarse particles fall quickly. Rain captures some. Buildings, leaves, roads, rivers, and ocean surfaces receive them. Higher particles travel farther. Above ordinary weather, sulfur dioxide changes through chemistry into sulfate aerosols. They are too small to see individually. Together they scatter sunlight. They do not understand what they are doing. No particle intends winter. No volcano intends famine. Geology contains causes without motives. This can feel frightening because there is nobody to persuade. It can also remove a burden. The Earth is not angry. The planet has not judged humanity. The catastrophe is not punishment. It is matter moving through physical rules inside an impossible premise. In the real world tonight, those rules prevent the premise from occurring. Volcanoes do not share a switch. One volcano may erupt while another nearby remains quiet. Systems separated by continents have no path through which to coordinate their pressure with second-by-second precision. Even the count of volcanoes depends on definitions because nature does not organize itself for a dramatic title. At any ordinary moment, some volcanoes on Earth are erupting. Most eruptions are small or moderate. Most affect limited regions. Monitoring agencies track unrest. Satellites observe plumes. Communities practice evacuation. Scientists study gases, earthquakes, ground movement, and past deposits. The real risk is local enough to prepare for. If you live near a volcano, the useful questions concern that volcano. Where are its hazard zones? How are warnings issued? Which roads lead away from valleys? What supplies should remain ready? What does the local observatory say? The useful response is knowledge, not fear of every mountain on Earth. Tonight's story borrowed an impossible trigger to reveal a possible vulnerability. Civilization depends on systems so ordinary they disappear from attention. Water arrives when a tap opens. Food appears in shops. Electricity waits inside walls. Medicine moves across borders. The sun rises with approximately the brightness expected. Most days, these are not miracles. They are infrastructure, labor, climate, and cooperation working quietly. The thought experiment makes them visible by removing them. You do not need to lose them in order to notice them now. Feel the surface beneath you. It may be a bed, a sofa, a floor, or a chair. Beneath the building lies soil, rock, and deeper rock under pressure and heat. The mantle below is not a liquid ocean sloshing beneath a thin shell. It is mostly solid material capable of moving slowly across immense spans of time. Heat remains from Earth's formation. Radioactive elements release more. Material rises and sinks. Plates move. Rock melts in particular settings. Magma collects. Sometimes it reaches the surface. This process has shaped the planet for billions of years. It built islands. It renewed crust. It released gases. It created mineral-rich soils. It destroyed landscapes and made new ones. Life developed on an active Earth, not a silent one. The ground beneath you feels still because geological movement is usually slower, deeper, or farther away than human senses can detect. Stillness can be real at one scale while motion continues at another. Your room is still. Earth rotates. Your body rests. Blood moves. A volcano can be quiet while crystals grow inside cooling magma far below it. The universe contains many kinds of stillness. None requires absolute absence of motion. Picture one volcano now. Not every volcano. Only one distant mountain beneath a clear night sky. Choose no famous name. Let it be a dark shape on the horizon, its upper slopes covered in snow or forest. A monitoring station stands several kilometers away. Instruments record tiny vibrations. A solar panel charges a battery. An antenna sends data toward a laboratory. The mountain is not erupting. The instruments do not make it safe by controlling it. They make people safer by helping them understand it. A scientist will review the readings in the morning. Tonight, the station works without needing attention from you. Wind moves over the slope. Cold air follows valleys downward. Stars remain visible above the summit. Inside the rock, pressure is ordinary for that system. Nothing is synchronized with distant mountains. Nothing is counting toward one global second. The imaginary map from the story can fade now. Let the red dots disappear one at a time. The Aleutians return to their separate weather. Kamchatka becomes distant. Japan, Indonesia, the Andes, Iceland, Italy, East Africa, Mexico, Hawaii, New Zealand, and the Cascades return to their own local geology. The ocean floor becomes dark and enormous again. Each system keeps its own history. Each chamber contains its own chemistry. Each fracture responds to its own stress. There is no single underground command. There is no planetary alarm about to turn every dot red. Let the operations room grow quieter. The printers stop. The emergency calls end. The screens dim until only one remains. On it, a normal seismic line moves gently from left to right. Small variations rise and fall. Nothing demands interpretation before morning. Nia is no longer standing beside the window. She has gone to sleep in a small room inside the center. Eli is not trapped in Portland. The ash never arrived. The first harvest did not fail. The pale volcanic sun exists only inside the thought experiment. Outside the imagined building, Colorado air is clear. Cars remain where people park them. Roads connect cities. Aircraft cross the night above clouds. Ships move through ports. Water waits behind dams and inside pipes. Fields hold crops beneath whatever season belongs to them. The ordinary systems remain ordinary. Somewhere, a real volcano may be erupting now. For nearby communities, it deserves attention and respect. For the rest of the world, it is one local event on a vast, active planet. This is the scale real geology provides. Not zero danger, not universal eruption. Specific mountains, specific hazards, specific knowledge, specific preparations. The distinction can settle around you more gently than vague fear. You do not need to monitor the mantle. You do not need to calculate sulfur. You do not need to protect the harvest before morning. Scientists, farmers, engineers, emergency workers, and communities will continue their real work whether you remain awake or not. The planet does not require constant attention from every person in order to keep turning. Let your breathing become the nearest system now. Air enters. Air leaves. No ash is falling inside the room. Let your shoulders rest more completely against whatever supports them. Let the weight of your hands remain where it is. The body understands gravity without explanation. It understands tiredness without models. It understands the gradual release of tension. One thought may rise like a small bubble through water. It does not need to erupt. It can reach the surface and disappear. Another may remain below awareness. There is room for both. The story crossed decades because the mind can cross time quickly. Your body remains here. No volcanic winter is passing through the next breath. No emergency year needs to be survived. Only a quiet interval before sleep. Imagine rain falling on the distant mountain. Water moves across old lava and through forest soil. Streams gather. The monitoring station records the sound as background vibration. In the morning, scientists will distinguish rain from earthquakes because they have learned the signatures of both. Knowledge turns noise into categories. You do not need categories now. Rain can remain rain. Rock can remain rock. The mountain can remain a silhouette. Far below, heat continues its patient work at a pace too slow to interrupt this night. Even real eruptions eventually end. Lava cools. Ash settles. Aerosols leave the atmosphere. Rivers cut new channels. Plants enter disturbed ground. The first life returning to ash is often small. A patch of moss. A root protected beneath soil. A seed carried by wind. Recovery does not begin with a forest. It begins with whatever can grow. Rest can begin in the same way. Not with perfect silence. Not with every thought gone. Only with one moment that asks less from you than the moment before. Then another. Let the dramatic first minute of the story move farther away. At 2:17, Every dot changed color. Now the clock has no importance. The monitors are gone. The emergency map has folded into darkness. The imagined ash has fallen from the air. The pale sun has brightened and set. Nia's long career has become a closed archive. Eli's message remains 4 words on a display in a future that never had to happen. I am inside. Breathing okay. You are inside this present moment. Breathing. Okay enough to rest. Outside. The real Earth carries mountains, oceans, cities, forests, farms, faults, and volcanoes through the night. Some ground is warm. Some is cold. Some is moving by fractions no person can feel. Beneath all of it, the planet holds together. Let the idea of every volcano become impossible again. Let each mountain return to distance. Let each distant plume dissolve into ordinary cloud. Let roads remain open. Let water remain clear. Let the next harvest remain beneath the future sun. Nothing in tonight's question needs to be solved again. The answer has reached its quietest form. Every volcano would not cover Earth in lava. The atmosphere and human systems would carry the greatest danger. Civilization could survive, damaged, and transformed. And the event itself has no mechanism in the real world. The remaining details can wait with the monitoring station until morning. Let the ground feel solid beneath you. Let the room feel still at your scale. Let the deep earth keep its ancient heat far below thought. There is no alarm, no red map, no ash against the window. Only this ordinary night on an active planet. A planet that has held life through billions of years of change. A planet that, for now, asks nothing from you. Sleep well.